My name is Mike Runge. I'm a research ecologist and a decision analyst at the U.S. Geological Survey, Patuxent Wildlife Research Center in Maryland in the United States. I work for the Department of Interior, for the U.S. Geological Survey, which is the science arm of the Department of Interior. And I spend a lot of my time helping wildlife and natural resource management agencies make decisions, complex decisions that have competing objectives and a lot of uncertainty. And I've found the value of decision analysis, the tools from decision analysis, as being really instrumental in the work that I do. So I want to talk about one of those tools today. It's called the value of information. And it's a tool that can let us evaluate when new information is important and relevant to a decision maker. This seminar is being done as part of the Environmental Decisions Alliance, an international alliance of folks that are interested in formal methods of decision analysis as they relate to environmental and conservation problems. So the question is here, do we really need to gather more information? We're called upon a lot to do this. We spend a lot of time thinking about what we're going to monitor and the research that we're going to do. And yet there is this dialogue that goes on that's quite interesting. You'll hear environmental scientists saying, look, these environmental systems are complex. They're so complex. We don't even know much about how they work, let alone how our management actions will affect them. So we need to reduce uncertainty, we need to monitor, we need to do research. At the same time, environmental managers will say, we have such limited resources and such large problems that every dollar spent on research is a dollar that's not spent on intervention or conservation. How do I know that when I invest in research or monitoring, that's going to improve the outcomes that I care about? That's going to help me reach my objectives better. In other words, will this information actually change my decision? And that's an important question. And that's the question that's central to this idea of value of information. And there is a tool. There is a set of methods in the field of decision analysis. These methods have been around since about 1961. They've been talked about on and off. Carl Walters, in his 1986 book on adaptive management, spends a lot of time talking about the value of information and how that indeed is the motivation for adaptive management. And yet, we haven't applied the concept of adaptive management well enough or often enough in our field. It's starting to change. The last 5 years have seen a proliferation of research in this topic, but we still have a ways to go. So the hope for this seminar is I can introduce you to the concept of value of information, share a bit of a case study, and maybe just put the seed in there about how we need to think about how information plays a role in our decision making. So let's begin. I'm going to show you 3 different ways of thinking about the value of information. Because I know people learn differently, and some people like math, and some people like diagrams, and some people like graphs, and so I'm going to show you all of those. This first one is a decision tree. And it sort of maps out the idea of the value of information from the standpoint of the decision maker and the series of decisions that that decision maker will have to make. So suppose I'm a decision maker, and scientists have come to me and said, look, think you should do some research. We think you should undertake this particular study because the decision you're about to make is affected by uncertainty. We think you should resolve it. And the decision maker has to say, well, look, if I undertake that study, it's going to delay action. There's costs of delay. And plus, the study is going to cost me something. Are those costs worth the improvement in my ability to make a decision? Well, the fallback position is actually not to do the study, right? And to make the decision in the face of uncertainty. Now, this is the field of risk analysis, and it's the bottom branch of this diagram. So if I don't undertake the study, then I have to choose an action without knowing how the world works perfectly, right? Without resolving this uncertainty that the scientists are proposing that I resolve. So I have to choose an action, A or B, without knowing whether Model 1 or Model 2 is the best descriptor of the system. And Model 1 and Model 2 might have really different predictions about how action A and action B do and how they help me achieve my objectives, the outcomes that I care about. But the field of risk analysis allows us to evaluate these things, right? I can think about what's the probability of Model 1 versus Model 2 being the case. I can think about what outcome 1 versus outcome 2 is likely to be. I can take a weighted average of those things. And so I can figure out what I expect to achieve if I take action A, or what I expect to achieve if I take action B. And I can choose the action which looks best in the face of uncertainty. And if I want, I can take into account my risk tolerance and all that. So there's a whole set of tools in the risk analysis world that allow me to make a decision in the face of uncertainty. And so that's the baseline I should be thinking about. If I don't gather this new information, well, that's fine. I'll just make a decision in the face of uncertainty. We do it all the time. And the question really is, if instead I undertake this study, how's it going to help me make a better decision? Well, essentially what happens is I get to find out whether model 1 or model 2 is the better descriptor of the system before I have to commit to an action. So I'm swapping the order of taking the action and learning about which model best describes the system. So that's interesting. I get the information first, and then I make the decision. And so presumably what this does, it allows me to choose a better action. Like, I don't know, let's say under model 1, action A is better. Under model 2, action B is better. Okay. Well, I take a risk in the bottom branch here because I'll choose action A not knowing whether model 1 is the best one or model 2 is the best one. And it might be model 1 is the best one and it all works out, but it might be model 2 is the best one and I've made a mistake. Whereas in the top branch, I'm not going to make a mistake. I'm going to learn which model is the best predictor of the world, and then I'm going to choose the action that's best for it. And the improvement in the expected value of my outcome is the value of information. The difference between the expected value of the top branch and the bottom branch is the value of that new information. Now, I have to compare that against the costs and the cost of delay and stuff like that. But at least it's a way of thinking about how much is that information worth to me as a decision maker. And it's worth noting that that's measured in the units that I care about. It's measured in the units of the performance metric I'm using to evaluate my fundamental objective or fundamental objectives if I've got multiple ones. And so it may not be in dollars, but it may be in acres of habitat improved. It might be in the increase in the probability or decrease in the probability of extinction of a threatened species. So it's measured in units that I care about. Let me show you another way to think about this. This is for the folks that really like math. We use some equations. So this is actually technically called the expected value of perfect information because I'm perfectly learning the truth of the matter about how the world works. There are other versions, expected value of partial information, expected value of imperfect information. I won't go into those today because really the key concepts are embodied in the expected value of perfect information. So suppose you have a set of actions indexed by A that you get to choose from. You have a set of models indexed by S and a probability distribution on those models, and that represents your uncertainty. The fact that you don't know which of those models is the case, that's your uncertainty, but you can describe that probabilistically. And you have a reward function given by utility U that encapsulate your objectives, the performance metrics, and if it's multiple objectives, it's got weighting on those. You can even fold your risk tolerance into that. The expected value of perfect information is given by this formula. It has two pieces. Let's look at the second term first, right? The second term says the maximum over the actions of the expected value over the models of the utility. What this says I should do, that second term says, well, take the expected value of the utilities, of the outcomes, over your uncertainty, and then choose the action that has the highest expected utility. That's what you do in the face of uncertainty. You calculate the expected value in the face of uncertainty and choose the action that has the highest expected value. That's what you do in a risk analysis. So that second term is just your expected value in the face of uncertainty. The first term is the expected value in the face of certainty. Because what happens is you're maximizing the utility knowing what S is. You know the model, and so you choose the action conditional on the particular model, on the hypothesis of the model or whatever represents your uncertainty. Now we have to take an expectation over that, because before we do the experiment, we don't know what we're going to find out. So we're taking an expectation using the prior beliefs in those different models, because we don't know what we're going to find out before we do the study. And so what you can see here is all you've done in this equation is reverse the order of operations of the expectation and the maximization. And that's the same thing as what we saw in the previous diagram of changing the order of, do you find out the information first or do you take the action first? And this is the way technically of calculating the expected value of perfect information. So it tells you the difference between the expected return if you resolve uncertainty before you make your decision, and the expected return if you make your decision before you resolve uncertainty. Okay, so that works great if you like math and you can follow the equations, and you're welcome to try it out on a problem of your own. Let me show you one more way of doing it that's kind of a graphical depiction of what's going on, and maybe this will convey some other nuances about value of information. Okay, suppose I've got two models and I don't know which one is the case. I've got model 1 and model 2. What I've graphed on the x-axis here is my belief in model 2. If my belief in model 2 is 0, so I'm on the left side of the x-axis, that means I fully believe model 1 is the case, and I don't believe model 2. If my weight on model 2 is 1, then I fully believe model 2, and I don't believe model 1. So this x-axis represents a degree of belief in model 2, and if we're in the middle, we're quite uncertain. If we're on either end, we're quite certain that it's either model 1 or model 2. Now let's suppose I have some predictions about how well I'll achieve my objectives if I take different actions, and depending on whether model 1 or model 2 is the case. So action 1, if model 1 is the case, gives me a return of H. If model 2 is the case, it gives me a return of A. So it does really well under model 1 and really poorly under model 2. I have another action, and I'm going to draw a straight line between these because that's essentially what an expected value is, right? This is the weighted average of H and A weighted by my belief in model 2, right? So the more I believe in model 2, the closer my expected value is to A. The more I believe in model 1, the closer my expected value is to H. And it's really just a straight line because a weighted average is a linear function. So we can just draw a line between these. Okay, so I've got a second action, action 2, that if model 1 is the case, I get return F. If model 2 is the case, I get return D. This one's a little bit more robust to uncertainty, right? It's not as sensitive to whether model 1 or model 2 is the case. There's a little difference, but it's not big. Okay. So as I have a third action, model 3, that does very poorly under model 1 and does pretty well under model 2. In fact, if I knew model 2 was the case, I would choose alternative 3 as the best one, and I would get return E. And if I knew model 1 was the case, I would choose alternative 1, and I would get return H. So what's curious is, okay, I've got two models. And okay, if model 1 is the case, I should choose alternative 1, action 1. If model 2 is the case, I should choose action 3. But there's this other interesting action that's kind of a bet hedging action. Action 2 is good in the sort of the middle here, between a belief weight of X and a belief weight of Y on model 2. In that range, action 2 has the highest expected value of the 3 actions. So that's really interesting, and that happens sometimes. Now, with perfect information, excuse me, I would never choose action 2, right? Because either I find out model 1 is the case and I choose action 3, or I choose I find out model 2 is the case and I choose action 3, or I have model 1 is the case, I choose action 1. But I've got this bet hedging strategy. Okay, so I'm gonna darken a line here that basically says if my belief in model 2 is less than X, I'm going to choose action 1. If it's greater than Y, I'm going to choose action 3, and if it's between, I'm going to choose action 2. And that is the smart thing to do somewhere along that line, depending on my belief in model 2. So if I have to make a decision in the face of uncertainty, that's what I should do. Okay, that specifies the expected value in the face of uncertainty, E sub u. Now, I'm going to draw a line here between H and E, because if I go ahead and gather information, do a study that resolves whether model 1 or model 2 is the case, I resolve uncertainty, I'm either going to find out that model 1 is the case, choose action 1 and get return H, or I'm going to find out model 2 is the case, choose action 3 and get return E. I'm only going to get H or E. I'm not going to get anything else. All those other things, those are downside risks that I'm now avoiding because I'm gathering that perfect information. So what perfect information does for you is it removes the risks of making a bad decision, of making a wrong decision, rather, of choosing the wrong action and getting the downside outcome. I'm only going to get either H or E. I just don't know which one it's going to be before I've done the study. So I'm going to draw a straight line because I'm going to take a weighted average, essentially, of H and E. Because prior to doing the study, my belief that I'm going to find out it's model 2 is given by the x-axis. And so I can use that belief weight to weight outcomes H and E and get this line here. And so the difference, so that's the expected value if I've got certainty, if I acquire certainty. And the difference between these is the expected value of perfect information. The difference between the thin black line and the thick black line is the expected value of perfect information. Now, there's some interesting properties there. The expected value of information gets quite small as you get quite certain. As you go over to the right and get closer to a weight on model 2 of 1, the difference between those lines is small. That makes sense. The more you know, the less the value of the remaining information. Likewise on the left. And it turns out that where the expected value of information is greatest, curiously, is always at an indifference point. So there's two indifference points here, one at x and one at y. The one at x actually has higher value of information, as it turns out. But here you're indifferent between taking action 1 and action 2. Doesn't matter. They have the same expected value at that point. And it's at those indifference points that you will have the highest expected value of perfect information. Okay, so those are just 3 ways of explaining the concept of the expected value of information. And I'll just say again, what it represents is how much you can improve the outcome of your decision in units that are relevant to the decision maker by resolving uncertainty before committing to action. So it's the value of information to the decision maker and their ability to achieve the objectives that they want. Okay, let's take a look at a case study. This is a case study I worked on with some colleagues a few years ago, and it involved a non-native species, brown trout, in the Colorado River in Arizona in Glen Canyon, which is the canyon, a couple canyons above Grand Canyon. Just to orient you a little bit, the Glen Canyon Dam, fourth highest hydroelectric dam in the United States, is up here on the Colorado River, and behind it forms Lake Powell. I should mention we're in the United States, in the Southwest, the arid Southwest, in the state of Arizona, northwestern Arizona. We've zoomed in here, and you're essentially following the Colorado River from Lake Powell at Glen Canyon Dam, all the way down to Lake Mead, which is formed by the Hoover Dam, 2 of the largest hydroelectric dams in the United States. And in between, you have this vast stretch of wilderness through Grand Canyon and through a number of Native American lands. And it's an incredible place. It's an incredible place for its natural resources, for its cultural resources. It's beautiful. There's unique species there, unique plants, unique rock formations. So this part of the story is really taking place in this upper part of the Colorado River between Glen Canyon Dam and Lee's Ferry. This is called the Lee's Ferry Reach. The tailwaters below a large dam often are quite cold because the water sort of stacks up really high behind the dam, and often the outlet pipes are low in that water column where the water is cooler, and trout like cool water. So there weren't trout trout were not native to the Colorado River, at least rainbow trout and brown trout were not native to the Colorado River. They were stocked in there as sport fish decades and decades and decades ago. And there's a healthy rainbow trout population in the Lee's Ferry Reach. There hadn't ever really been too many brown trout, but there had been some. Now I want to mention another part of this map here. If you look kind of on the right here near Reach 2, where the Little Colorado comes into the Colorado River, this place here is the stronghold for a native species of fish called the humpback chub, which is listed on the endangered species list in the United States. And really it's threatened because the Glen Canyon Dam changed the hydrology and changed the temperature profile of the Colorado River when it was built. And it's just the environment's not as well adapted, or the fish aren't well adapted to the new environment. Furthermore, these non-native species, the rainbow trout in particular, but also brown trout, compete with the humpback chub and also possibly predate them. Well, certainly the brown trout are a predator of humpback chub, and rainbow trout in some circumstances are a predator of juvenile humpback chub. And so these non-native fish are a threat, are part of the threat to humpback chub, this listed species. Okay, so that's a concern. There's also a bit of a concern about brown trout and its competition with rainbow trout. Well, okay, so the story begins maybe in about 2014 when, well, it begins later than that, but it appears that something happened around 2014. We started to see more brown trout in the Lee's Ferry Reach of the Colorado River. This is, these graphs show the catch per unit effort. So the number of fish caught per hour of brown trout of 3 different size classes. And this started to be worrisome because there was a concern that if brown trout were going to be established in Lee's Ferry and start having a really productive population there, those brown trout could then swim back downstream and be a threat to humpback chub. They might also disrupt the rainbow trout fishery, which is an important fishery in the Lee's Ferry Reach. So what was going on? It appeared that some brown trout immigrated from downstream up to the Lee's Ferry Reach sometime around late 2014, adults, right? And then soon thereafter, they started reproducing pretty effectively. And so you see a bump up in the size class 1 fish in about 2015, especially 2016, size class 2 fish in 2017. And it's possible they're now starting to recruit into the adult age class. So you get this big bump in brown trout. That was a concern to people. It was a concern especially because a new operating plan for Glen Canyon Dam had just been put into place. And people were concerned that this might disrupt how the dam was supposed to be operated in terms of how it was affecting downstream resources. So we convened an expert panel to think about this problem and to think about what might be going on, and we worked with the management agencies to talk to them about what they cared about to do a bit of a decision analysis. So the first question is, why do we have a problem? So we developed some alternative causal hypotheses for why brown trout are increasing at Lee's Ferry. So this is, okay, remember, we're talking about the value of information. So part of that involves articulating uncertainty. So we're articulating uncertainty here. The motivating observations were, it seemed like there was immigration of brown trout starting in late 2014 into Lee's Ferry. Why? Second, there's increased reproduction of brown trout in Lee's Ferry on a per capita basis beginning in about 2014. Why are they being more successful? So there's more adults, spawning adults, and they're more successful. Why? Some suspicious correlations. There's some other things going on at the same time that might have been related. There had been 3 consecutive fall high flow releases from the dam in 2012 through 2014. These are high flows through the dam at particular periods of time to try to mimic some of the conditions that would have existed before the dam was built, when there would be really high flows that would move a lot of sand, change the riparian vegetation, affect the downstream species, aquatic species. So the Bureau of Reclamation and the Park Service wanted to mimic some of these conditions to try to restore some of the ecosystem function in the Colorado River. There had also been a trout removal project in Bright Angel Creek, which is downstream, considerably downstream of the Lee's Ferry Reach and downstream of the Little Colorado River. So this creek is a tributary to the Colorado River, and there had been these trout removal projects going on from 2012 to currently. Some thought about the way that worked might have caused trout that didn't get caught up in that project to move upstream. Concurrent reduction in rainbow trout numbers in Lee's Ferry about the same time as the brown trout numbers were increasing. There had been river-wide fish condition decline. So there were some strange things that were happening at the same time, and so there were some questions about whether they're related. So this expert panel came up with 7 hypotheses. Actually, they had plenty more than this, but 7 that they really wanted to focus on. And they involved whether the brown trout, the change in dynamics of brown trout was caused by a change in immigration, a change in recruitment, or both. And there's various reasons for these. I won't go into the details about what these hypotheses are, but they were causal mechanisms that, that made sense, but for which we didn't have a lot of evidence, or we had no conclusive evidence to tell us which of these is the case. There were some judgments, there was some expert opinion about which were more likely than others, but we didn't know. And these different hypotheses have relevance. Or well, we wanted to investigate whether they had relevance for decision making. So we developed these different hypotheses about how the world might work. That's our uncertainty. Question is, what can we do about it? Well, are there actions we can take that might reduce the number of brown trout and Lee's Ferry? And does that depend on the causal mechanism by which brown trout were increasing? And so we looked at 6 strategies. One was status quo. One was incentivizing fishing of brown trout by maybe having a bounty or prize fish, or some regulations that would motivate people who are fly fishing to focus on brown trout and remove those brown trout from the river. There was an option number 3 that essentially the status quo, but just eliminated the fall high flows in case that was a trigger for brown trout immigration. 4th one, where switch those high flows to spring and do more in the spring under certain kinds of conditions, and that was thought to possibly be of less benefit to brown trout. There were some brown trout management flows, number 5. These trout management flows are designed to hit trout at the reproductive period, and so you have some flows that encourage them to lay their nests, and then you drop the water and desiccate those nests at a key point, and so you try to reduce the reproduction that way. And then finally, there was an option that involved electrofishing, which is when you go in with boats and you use you sort of do this electrofishing, which stuns the fish, and then you just kind of pull the brown trout out and remove them from the river and use them for some kind of beneficial use. So these were ideas that people had talked about possible ways to deal with this problem. And we wanted to look at, well, does the action you choose depend on the causal mechanism for the brown trout increase? So we built this population model. Charles Yakulik built this population model for brown trout, and it has all the kinds of things that, survival rates and reproductive rates and immigration rates, and those are all affected by these different hypotheses, and those hypotheses interact with the different alternatives, and so we can use this to predict what might happen under different management actions and under different hypotheses about the causal reasons for the increase. Okay, so there's a model behind this influence diagram, and it took into account uncertainty both in these hypotheses, but also in the underlying parameters. And there was a lot of uncertainty. I mean, there's a lot we don't know. The baseline uncertainty is pretty high. I mean, the confidence intervals are large. I mean, a factor of 4, let's say, in terms of what we think might happen under any combination of hypothesis and alternative, because there's a lot we don't know. But we wanted to zoom in on, okay, what's the role of these different causal hypotheses in the decision about what to do? And so this table shows, and a lot of times a value of information calculation will have a table like this, where it's got the hypotheses that represent uncertainty here in the columns, and the alternatives that represent the actions you can take in the rows. So for instance, that first row shows you what the expected number of brown trout, adult brown trout, averaged over 20 years would be if you took the status quo action under each of the hypotheses. So 13,200 under hypothesis 1, 20,600 under hypothesis 7. And the last column is the weighted average of those values, weighted by our belief in the different hypotheses. So the experts didn't believe all the hypotheses were equally likely. They thought hypotheses 1, 4, and 7 were more likely than 2, 3, 5, and 6. So an unequally weighted average of these numbers produces that last column. Now we can look down these columns and find some interesting things. If hypothesis 1 was the case, and we want to minimize the number of brown trout, then the best action we can take is this enhanced spring flow. And that would produce 6,200. That's our expected value, the expected number of adult brown trout over 20 years. If hypothesis 2 is the case, then the smartest thing for us to do is this trout removal action, action number 6, and that's got the lowest value in that column, 4,800 brown trout. We can also ask, okay, so this bottom row shows you, just repeats the numbers that are highlighted, right? It shows you if you choose the best action under each hypothesis. That bottom row shows you the expected number of brown trout in Lee's Ferry on average over 20 years. Yeah. Now, and interestingly, only 2 actions appear as optimal, right? Either enhanced spring flows under hypotheses 1, 4, and 7, or trout removal under 2, 3, 5, and 6. Now, this last column shows what we should do in the face of uncertainty. In the face of uncertainty, the best action, the action with the lowest expected value, is action number 6, trout removal, with 8,299. So the idea there is what you're doing is you're choosing you're taking an average across the uncertainty, and you're choosing the action with the lowest average in this case. So that's what we do in the face of uncertainty. Okay, so that's the action that's best in the face of uncertainty. Now this number 6,704 is an interesting one. That's the average of the best. This 8,209 is the best of the averages. The 6,704 is the average of the best values. And the difference between those is the expected value of perfect information. And it essentially says that in the face of uncertainty, what we should do is we should do trout removal. And we should expect to have about 8,300 trout on average over the next 20 years. But if we can resolve uncertainty first, the expected number of trout we'll have, we'll either do enhanced spring flows or trout removal. We won't know that till we've resolved the uncertainty. But once we've resolved the uncertainty and committed to the appropriate action, the expected value is 6,704. That's a decrease of 1,600 fish, about a 19% reduction in the expected trout numbers. That's the expected value of perfect information in this case. The way we've said it is, it's conditional on the context. It's conditional on the alternatives that you've set up, on the hypotheses you've considered, the uncertainty associated with them. But this is a measure of how much we can improve management if we could reduce uncertainty. Okay, so a couple of thoughts. First, there's a lot of inherent uncertainty, and the causal explanation is not clear. There was a single large immigration event. Will it be repeated? The reproductive rates are higher, but we don't know why. The projections, even under the status quo, are quite uncertain. So there's a lot of scientific uncertainty. Is it worth reducing that uncertainty? Yes, it is. You'd make different decisions depending on which hypothesis is the case. But the gain in management value isn't that huge. It's about 20%. We've got a lot of things we can do that are pretty robust options anyway. So there's management actions that could hold things in check with the brown trout, even if we have to do them in the face of uncertainty. So Basically, the big gains come from not doing the status quo, but doing something else because you're thinking about brown trout. Above and beyond that, there's another 20% you could reduce things if you could resolve the remaining uncertainty. So if you want to see the details of this, is written up in a report. That's a USGS Open File Report 2018-1069 that some colleagues and I wrote. You can just Google that report and download a PDF if you want to see the sort of gory details of how we did this work. So some thoughts. There's a conundrum here. Seems like a paradox. In many environmental applications, there are large scientific uncertainties in the predictions. But we've found, a number of us, doing this kind of work over the last decade or so, that when we've calculated the value of information, it's often fairly small, smaller than we would have thought, 6%, 9%, 15%. Yeah, you can improve the outcomes often, but not that much. So why is that? Why might there be a lot of scientific uncertainty, but not as much management uncertainty? Well, scientific uncertainty and decision uncertainty are not the same thing. They're just different things, right? Scientists cares about the magnitude of the uncertainty in the predictions. The decision maker cares about the uncertainty and the action to take. Those aren't the same thing. Second, maybe we know more than we think. Often I think when we say, are we uncertain? How much do we know? You know, we'll think about all the things we don't know, but we won't really tabulate the things we do know. And in fact, we often know a fair bit about how the system works. And finally, I think in contentious situations, sometimes people use uncertainty as a wedge. So we overemphasize how much uncertainty there is, perhaps as a tool in the negotiation process if we're not agreeing about what to do or what the objectives ought to be. Okay, so can we learn more about this? Can we learn more about why value of information might be smaller than we often think it is? Well, let's go back to this kind of diagram where we're showing a couple actions and a couple models. So here's an example where same setup as before. I've got action 1, does really well under model 1, does very poorly on model 2, and it's quite sensitive to that uncertainty. And so, okay, fine, if model 1 is the case, you should do alternative 1, but there's a really big downside risk if model 2 is the case. Whereas here now we've got an action 2 that's kind of robust, right? It doesn't vary much with uncertainty. Yeah, it's a little better under model 2 than model 1, but it's not that big a deal, right? And let's say further that we had about a 2/3 belief in model 2. Well, in this case, we're sitting about here where this X is, and the expected value of perfect information is kind of small. It's kind of small because we got a robust option, and we've got a fair amount of information, at least 2/3, 1/3. You know, we've got a 2-to-1 belief in model 2 over model 1, and that puts us far enough to the right that there's not a lot of gain. We should just do alternative 2 and live with it. That's fine. And even if our uncertainty were such that we were over to the left here, where this indifference point is, that value of information is not even all that big either, right? Because we've got this robust option in there, and so maybe that's the kind of thing that's often going on, is we have a decent option in our toolkit, and when we have that the value of information, you know, maybe is not as big as you think it would be. When is value information largest? Expected value of perfect information, you can kind of show this algebraically. You can prove this, that the value of information is largest in this setting where all your actions have some really serious downside risks. So notice neither of these are robust actions, actions 1 and action 2. If you're right, great. If model 1 is the case, you choose action 1, great. If model 2 is the case, you choose action 2, great. But if you're wrong, and you choose the wrong action for the way the world works, then there's really big downside risk. And furthermore, let's assume that our uncertainty is so great that we're right at the indifference point. And so then we get a fairly big expected value of perfect information. And Okay, so this is, you and I should prove this, that expected value of information is greatest when you've got these two conditions. The first one is that the upside downside risk, on both sides of these axes, whether it's model 1 or model 2, is the same, right? You've got, essentially the difference on the left side and the difference on the right side here are the same magnitude. Condition number 1. Condition number 2 is your knowledge puts you right at the indifference point. So let me put that another way. EVPI, the value of information, is greatest when the cost of being wrong is high for all actions and when there's a good chance of being wrong. But to the extent that these conditions are not met, then the expected value of information gets smaller and smaller. And so I think maybe that's a useful insight for thinking about why it is that perhaps value of information is not always as big as we might think it is. Okay, so just by way of summary, scientists and decision makers view uncertainty differently. That's very important, and it's important to realize that the sort of disagreement I painted a picture of in the first slide arises because these two groups of people see uncertainty from a very different lens. For the decision maker, the relevant question is whether new information might change the choice of action. And I think we should focus on that. We should be aware that that's, for a decision, in an applied decision context, that's how we should analyze uncertainty. There is a formal way to do this. There's a formal way to calculate the value of information in units that are meaningful to the decision maker. And what it involves is first carefully structuring the decision and doing a deliberate analysis of the uncertainty. And that can provide guidance. That can provide guidance to the decision maker about, 1, what to do in the face of uncertainty, and 2, whether it's worth reducing that uncertainty or not. Are there some emerging insights? Well, the value of information often isn't as large as we might think it should be. And I think that conundrum is causing some of us to really think about, well, what causes information to be valuable, and what are the conditions when we think it really would be important to gather more information. And those are useful conversations to be able to have with decision makers. So I want to thank you for joining us at the Environmental Decisions Alliance today and listening to this seminar. Here's some additional resources, just a handful of papers that have been published in the last few years about the value of information in an environmental decision context. These are all quite interesting, and I think you'll find them valuable if you want to follow up. And they also have a lot more pointers into the literature and a lot more sort of details about these concepts. You're welcome to email me if you've got questions or want to engage in some discussion. You can also follow me on Twitter, where I sometimes tweet about these kind of topics. So thanks again. Appreciate your joining in, and good luck.